Welcome to lecture 9.1. Now we are looking at something a little different than what we've been looking at before, and this is something called vectors. So what is a vector? Well, a vector is a line segment with a magnitude, which we would also call length, same word for length, and it also has a direction. Okay, so it's a line segment, but it has two things, a length and a direction that it's headed in. It has an initial point, which we would call the tail. So I'll go ahead and highlight that over here, the tail. And a terminal point, once again thinking terminate, terminal point, which is the head, and a terminal point. Okay, so here we go. We'd have our line segment. It's got a magnitude or a length. It's headed in a direction. Which direction? Well, we look at that little arrow right there. It's headed in that direction. And it has the initial point, and then the terminal point, which is the head. Alright, so if we have two vectors, u and v, they are considered equal if they have the same magnitude, so the same length, and the same direction. So if they're the same length and they're also headed in the exact same direction, they are considered equal. And the magnitude of a vector u is its absolute value. Okay? So keep that in mind. The magnitude is its absolute value. Now, the zero vector, 0, has no magnitude or direction. Okay, the zero vector basically just is like a little dot 0. Doesn't have magnitude or direction. And the magnitude is called a scalar, which means it is a real number. Alright, so let's take a look at some geometric representations of the sum and difference of two vectors. Okay, so oftentimes we'll be looking at these two different line segments and comparing what we'll do with them. So we'll either be maybe adding or subtracting them, one of the things we'll be doing. So if I have a vector u and a vector v, if I add them, which basically is when I put the head of one against the tail of the other one, I'll get the resulting addition of u plus v, headed in the direction. Okay, so notice they should be heading in the same direction when you're doing the addition. Another way to look at that is if you have your u value and your v value, and you set them up when their tails are against each other, if you create a parallelogram perfectly in that direction, so perfect parallelogram, you make a parallel line to this one, and then you make a parallel line for your other one. Then, right in between here, that is going to be the u plus v. Okay, so once again, these two here are two different ways of showing the addition of two vectors. Okay, two different ways of showing what the addition would look like. Now, the other thing we would look at is the subtraction of two vectors. So if I have vector u heading in this direction right there, so the arrow is here, and then, sorry, that's v. And then if I have vector u heading the other direction here, with its arrow in that direction, when I subtract the two of them, I'll get a vector heading this direction, right there. You can't really see the arrowhead that well, but that would be the subtraction of the two vectors. Alright, so vectors in the coordinate plane. Once again, the coordinate plane is the xy plane. So if we have a vector v, it'll be equal to a comma b. And please note here, it's a little different than regular coordinates. Why? Because we have, instead of parentheses, we have these little angular parentheses. So vector v has a horizontal component, which we call a, and a vertical component, which we'll call b. If v is represented in the xy plane with the initial point p of x1, y1, so let me go ahead and draw this out. So if we had a vector, this would be p of x1, y1 at the tail, and then the terminal point q, x2, y2, then what do we know? Well, then the vector AB is going to equal what? Well, the subtraction of those 2 points and the subtraction of those 2 points. So we go ahead and highlight that. That is how we would find our vector. We take the subtraction of the x values from the head and the tail, and then the subtraction of the y values from the head and the tail to find our a and b values for our entire vector. Now that is for the vector, but the magnitude of our vector is going to be, and this comes from the Pythagorean theorem, because if you'll notice, let me take a small detour, we can create a triangle with this, right? We can create a right triangle. So because of that, we can use our formula, a squared plus b squared equals c squared, and we can use that to find the magnitude. Where the magnitude is the absolute value, okay, that means it's going to be positive, of the square root of our a value and our b value. So note, if an initial point is not given, what does the initial point mean? Well, if we are not given this value here, we're allowed to assume that our vector is starting at the center, otherwise called the origin, of our graph. Okay, let me just go ahead and show what that is. So if we had our xy plane, we're allowed to assume it starts at the origin unless they tell us otherwise. Alright, so let's take a look at an example. Sketch the vector q to p. Okay, so q is going to be our initial and p is going to be our terminal. For, well, p is a half, 3. So that's my x value, my y value. And then q is negative 2, 8, and find its magnitude. Okay, so this is a little tricky here because they kind of switched in p and q on us. But our initial value is going to be q, because we're starting at q for the vector. Notice the direction that it has for the vector qp. So starting with q. Q is going to be my initial, so that means these are going to be my x1, y1s. And p will be my terminal, so x2, y2. Alright. Plugging that into our equation, we get v equals, and our x2 is going to be a half minus our x sub 1, comma, and then our y sub 2 is 3 minus our y sub 1, which is 8. So that'll be a half minus 2, which will be 5 over 2, and then negative 5. So that is my vector v. So why are we finding this? Well, that gives me my a and my b values. A and b. Actually, let me change the color. A and b. And that I can use to find the magnitude. So my a value is 5/2, and my b is negative 5. And my vector is going to equal, well, according to our information here, the absolute value of the square root of a squared plus b squared. So let's see. The magnitude, we use the absolute values to indicate magnitude. It's going to equal the square root of, we have 5 over 2 squared plus negative 5 squared. That gives me 25 over 4 plus 25. So to create the same denominator, we'll go ahead and multiply the top and bottom of this by 4, which means we'll have 100 plus 25. So that'll equal the square root of 125 over 4. Simplifying that down, we'll end up with 5 root 5 over 2. Almost ran out of room there. Squeezing it in. Okay, so that's the magnitude, the absolute value symbol over the v. Now we just have to sketch our vector. So let's go ahead and take a look at it here. Well, what are my points? I have a 2 and an 8. Okay, so let's go ahead and see this. 1, 2, 3, 4, 5, 6, 7, 8 for the y. And we go down to negative 2 for the x's. 1, 2. And then we also go up to 3 for the y. So, let's see, where is q? Q is negative 2, 8, so right up here. And according to this, that was the initial point. Should have done that in red. And then our terminal point was half 3. So let's go ahead. Here we have 1, so half 3. Right there. P half 3. And let me just go ahead and rewrite that here. Negative 2, 8. So our Q was the tail, and P was the terminal point. So it starts here, and then it heads in this direction. And make sure to include the arrowhead to indicate the direction it's going in. And that right there is our vector QP. Okay, so we sketched our vector, and we also found the magnitude. Once again, in order to find the magnitude, you do need to use this formula here to find your a and b values. Then you can plug that into that formula there to find your magnitude. So let's take a look at something called vector operations. So suppose C is a scalar, which recall a scalar just means a number. And U, or we have the vector U, is U1, U2, so we have our A, B values. And then vector V is our other A, B values. Then, well, if we have the addition of the two vectors, we just add up their A values and their B values. Okay. If we have the subtraction of two vectors, we subtract their two values. Careful here, though. Whichever vector comes first, that should always come first for the subtraction values. And then if you have some regular number, so a scalar C, being multiplied to your vector, all that you do is you multiply that C in to each of the A, B values. Just multiply it right on in. Pretty similar to what we know for most of our rules of addition and subtraction and multiplication. So now, example 2. Let U equal 2, negative 5, and V equal 3, 8. Find A, U plus 3V, and B, 4U minus 5U. Sorry, for V minus 5U. So looking at A. Well, we're going to have U plus 3V, and what's that going to equal? What is U? U is 2, negative 5, plus 3 times V, which is 3, 8. Let's see. Well, first, let's go ahead and do the multiplication, which means we're going to go ahead and multiply that 3 in to all of the values here. So it'll be the 3 times the 3 and 3 times the 8. So that'll be 2, comma, negative 5, plus 3 times 3 is 9, and 3 times 8 is going to be 24. Now, all we have is the addition, which means we're just going to go ahead and add up the A values, which would be the 2 and the 9, and then add up the B values, which will be the negative 5 and the 24. So 2 plus 9 is going to give me 11, and negative 5 plus 24 will give me the 19. And there we go. I have added those two vectors together. Once again, please note that it is important you continue to use the proper parenthesis notation, which is not really parentheses, it's those little angles. So please make sure to keep that going throughout your solving. Now let's take a look at B. We want 4V minus 5 times U. 4, okay, well what is V? V is 3, 8. Minus 5U, and U is the 2, negative 5. Well, before we do anything else, let's go ahead and multiply those scalar values into our vectors. And then we'll get, so 4 times 3 is 12. 4 times 8 is going to give me 32. Minus, okay, so we'll have minus 5 times 2 is going to give me the 10, and then 5 times negative 5 will be negative 25. Okay, so we've done all of the multiplication. Next thing to do is the subtraction. So we'll subtract the A values from each other, and then we'll subtract the B values from each other. So that'll be 12 minus 10, which will give me 2. And then that'll be 32 minus, minus a negative 25. Those two double negatives become a positive, so we'll end up with a 57. Okay, hopefully pretty straightforward so far. If not, once again, always feel free to email me for an office hour. Alright, summary. So properties of vector operations. So suppose we have the vectors u, v, and w, and a and c are scalars. Then the following properties hold for vectors in any number of dimensions, whether it be 2-dimension, 3-dimension, and so on. So we have something called the commutative property. This is pretty similar to what we use in general with addition and subtraction and so on. If you have u plus v, it's the same thing as v plus u. And then, for these ones, it doesn't matter which ones you add first. It's alright. And then, if you have a vector and you add 0 to it, you'll still get that vector. Or, if you have a vector and then you add the opposite of that vector, you'll get 0. Just like, for example, if you had 2 and then you took 2 away, you'd end up with 0. And then this one right here for 5 is just like the distributive property for a value. You just get c to both of them. And then the same thing in the other direction. If you have a v on the outside, you can just go ahead and plop it in. If you add, or if you multiply your vector by 0, you'll end up with 0, just like in numbers. And if you multiply a number to the 0 vector, you'll still have the 0 vector. Remember, the 0 vector does not have a magnitude. And then if you multiply your vector by 1, you'll get back the same vector. And lastly, if you decide to multiply your vector by a c value, or if you multiply these two values first and then multiply it by your vector, it's the same. So these things are pretty much items we already know in the regular number world we've been using before. So it's really nice to know that it works well with vectors. Now, a unit vector is a vector that has a length of 1. The vectors I equal to 1, 0, so the a value is 1 and the b value is 0, and j, 0, 1 are called coordinate unit vectors. Very important to remember. Coordinate unit vectors. Vectors can be expressed in terms of the unit vectors as, so if we have a vector, which you call AB, then the a times I plus b times j is a way we can represent that. So instead of using the parenthesis values, we can go ahead and represent it with a j and an I. Vectors ai plus bj and ci plus dj are equal if and only if a is the same as c and b is the same as d. Basically, it means if a and c are the same and b and d are the same, then the vectors must be the same vector. All right, example 3. Verify -3, 10 is equal to -3i plus 10j. Okay, well, starting with the left-hand side. We know that -3, 10 is the same thing as -3, 0 plus 0, 10, right? Because if I just added the a values, I would get that -3, and if I added the b values, I would get that 10. Okay, so then this is the same thing as -3 times 1, 0. I just factored out a 3. Plus 10 times 0, 1. Right? If I just multiplied that 3 out, I would get what I had above. And we already know, if you remember, that that I is equal to 1, 0. So that is I. So we have -3 I. And okay, so one thing to note, when I write my I, just because I don't want it to look like a 1, I usually put a little tail in the opposite direction. So -3 I plus, and we already learned that j was equal to 0, 1. So that value, I'm going to go ahead and switch that out, or substitute it out for j. 10j. And there we go. They are equal. We have done what we needed to. They are the same thing. Okay, so components and trigonometry. Let v be a vector with the initial side at the origin. Okay, so if we had our xy plane, we have the initial side at the origin with a magnitude, absolute value v, and direction of theta, the smallest positive angle in a standard position formed by v and the positive x-axis. So once again, if we're looking at the x-axis, there are two possible angles, this one or this one. But what do we want? We want the smallest one. So we would take this angle right here. That would be theta, the smallest distance between our vector and the x-axis. Oops, wrong color. There we go. Then what do we know? Well, the vector AB will be equal to AJ plus BJ, which is going to be the same thing, or equal to our magnitude times cosine theta I plus the magnitude times sine theta j, where A is equal to magnitude cosine theta I and B is equal to the magnitude of sine theta j. Alright, so that's just the introduction of how we mix the vectors with trig. So example 4, a vector has length 4 and a direction of pi over 3. Find the components and write in terms of I and j. Well, we are given pi over 3, so we're definitely going to go ahead and focus on using this formula. So let's go ahead and use v equals absolute value of v, or the magnitude, cosine theta I, plus the magnitude of v, sine theta of I. Alright, so our vector v, we'll go ahead and do vector with v hat. Well, what is our magnitude? Well, it doesn't state what the magnitude is, but be careful. Remember, length and magnitude are the same thing. So it's a length 4, which is going to be our magnitude. And then our theta is pi over 3. And once again, we do not put I and j in. Just remember, I is the same thing as 1, 0. And j is the same thing as 0, 1. So we're not going to be swapping those out for something. Okay, so magnitude, so 4 cosine of pi over 3, I, plus 4 sine of pi over 3, j. Oops, I did that wrong there. That should have been a j earlier. Alright, so now we just have to evaluate cosine of pi over 3 and sine of pi over 3. So at pi over 3, what is cosine? Well, pi over 3 cosine is a half, and sine is root 3 over 2. So 4 times a half I plus 4 times root 3 over 2 j. And we get, it's going to be 2I plus 2 root 3 j. Now one thing to note here, when we're talking about vectors, we're going to go ahead and include the arrow on the top. It is a lot to write, but it is the correct terminology, okay? So go ahead and keep the arrows on top for the I and j. Alrighty, and there we have our vector. Written in terms of I and j. Example 5. Sketch the vector. Find the direction of the vector. For sketching this, let's go ahead and rewrite it in the normal terminology we have. So that is going to be 1 negative root 3. Alright. Let's go ahead and do a small sketch of that. So starting from 0, 0, we're going to go 1 in terms of the a values, and then negative root 3. So 1, negative root 3. And here we have our vector. The question is next, what is our theta? Well, how could we find theta? Does this look familiar? It does. We can use tangent to find the hypotenuse, or theta. So tangent of theta is going to equal the opposite over adjacent. So remember SOHCAHTOA. So opposite is going to be negative root 3 over adjacent, which is 1. So the question is, when is tangent of theta equal negative root 3 over 1? Well, that is at theta equals 5 pi over 3. So what is our direction? The direction is, oops, there should be a 1r there. Direction is 5 pi over 3. And there we go. We have our vector and the direction. One thing to note, I forgot to mention it. If you have a vector that includes I and j, it's always going to be at the origin, okay? So if it includes I and j, it's going to start at the origin. Small side note there. Okay, so example 6, sketch the vector. Once again, if we have I and j, we start at the origin. Find the direction of the vector. So same type of problem, we're going to sketch it and find the direction. So let's go ahead and rewrite this in a form that's easier to graph. That is going to be negative 4, 7. Okay, so negative 4, 7. Alright, or negative 4, and then 7. Or in this case, it's going to be here, 7. So we can create that angle. Now we just have to find theta. Well, how do we find theta? Once again, we're going to go use tangent. So tangent of theta is going to equal, well, opposite over hypotenuse. Sorry, opposite over adjacent. Which means we need to figure out, well, we don't know what that is on the unit circle. So we'll go ahead and use tangent inverse. So theta is going to equal tangent inverse of negative 7 over 4. Okay, and then Since that's not on the unit circle, we'll go ahead and plug that into the calculator. So theta is going to be approximately equal to negative 60.25. Okay, and the negative there because we're heading in that direction, creating that angle. Alrighty, there we have. Oops, let's go ahead and remember that arrowhead for the direction of our vector. Okay, so a vector may model the velocity of a moving object. The direction of the object is the direction of the vector. Okay, so if you have an object flying in this direction, the vector would also be heading in that direction. The speed of the object is the magnitude of the vector. Okay, so speed and magnitude, and once again, magnitude is also the same as length, if you recall. So example 7, a plane heads due east at a speed of 400 miles per hour. It experiences a crosswind. So what is a crosswind? Well, that means it's moving across the plane. So it's not pushing from behind the plane, and it's not pushing at the front of the plane. It's along the side. In the direction of north 30 degrees east, find the true velocity of the airplane, its speed, and its direction. What is true velocity? Well, true velocity means the velocity of the plane with the effect of the wind. So it's with the effect of the wind. All right, so go ahead and draw a small graph here on what this looks like. Okay, so I have my coordinate plane, and then what do I know? A plane is heading due east, so it basically means exactly east. So this is where a plane is heading, due east. And then what do we know? It experiences a crosswind. And the crosswind is blowing in the direction of north 30 degrees east. So we go north, but then 30 degrees east, and that's our crosswind. Okay, so this is our crosswind. And you could have multiple vectors of that heading in this direction. Let me just go ahead and erase those for the sake of the graph. Okay, so what are we looking at here? Well, the plane heads out in one direction, but then it's being buffeted by the wind in another direction, right? So as the wind is coming up from this direction, it's going to hit the plane and sort of shove it up, right? So we'll have this new vector sort of heading this direction because the plane gets buffeted up by the wind, or it's getting a crosswind. So let's go ahead and start labeling these vectors. Let u, the vector u, equal the vector of the plane. We have a 400 miles per hour, or the magnitude. Once again, remember, speed is magnitude. And then we'll call w the wind, which we have at 50 miles per hour. So that is the magnitude of the wind. And then we are going to be looking for, I'm going to keep that as, I'm going to call that v. So v is the wind. And then w, the vector w, is going to be the true velocity. Of the plane, or where it really is headed. So this is going to be w, where it's really headed. V, or u, is where it took off, and v is the wind that is bothering our plane. So how do we figure this out? Well, if you'll notice, we'll also have that vector there, v, that vector for v. So we're going to find our u and v values and then add them together to get the velocity of the plane. We'll just find this vector here, add it to this vector here, and then we'll end up with the true velocity. Alright, so what do we need now to find everything out? Well, for the formulas for u and v, u is going to equal, we need the magnitude cosine theta I plus the magnitude sine theta j. You can do the hat or you can do the arrow. And then for v, we need the same thing. So magnitude cosine theta I, magnitude sine theta j. Well, we have the magnitude for all of them. So this is my magnitude here for the plane. And then we also have the magnitude for our wind right there. Now what we need is the theta values for both of these. Well, what's the theta value for u? What is the distance that that vector has traveled from the x-axis? Well, in reality, it hasn't moved from the x-axis, right? It's actually on the x-axis. So theta for u is actually going to be 0. Aha. Now what is theta going to be for v? Well, if you recall, it's 30 degrees in that direction. But that's not what we want for our vector. We want to figure out how far it is in this direction. So we'll just take 90 minus 30, and we'll find that angle, and that will be 60 degrees. So theta for our v value, or the wind, theta is going to be 60 degrees. Alright, so let's go ahead and plug those in. So u is going to equal, well, our magnitude is 400 times cosine of 0, our I value, plus the magnitude, sine of 0, j. Oops, it is squishing into the other one there. V is going to equal our magnitude we have is 50, cosine of 60 degrees, I, plus our magnitude again, sine of 60 degrees again, j. Alright, and then, so simplifying this out, what will we get here? We're going to have 400 I plus, now you could just write 0, but because we want to always have I and j values, we're going to write out the 0j. So keep that in mind. If you ever have a j value, just still stick to writing the 0. And then my v is going to equal, well, that's going to be 50. Cosine of 60 is a half I plus 50 sine of 60, which we know is going to be root 3 over 2, j. And then v is going to equal, so 50 half, so that's 25 I plus 25 root 3 j. Okay, so we have found v and j. Or sorry, u and v. We found these two vectors. Let me just go ahead and highlight them so you remember what they are. So this is this value right here, which we know here. And then this is my v value right here, which we have is here. So now we want to find w. Well, how do we find w? Well, it's going to be the addition of those two vectors. So w is the addition of those two vectors. Go ahead and write that down. So w is going to equal u hat plus v hat. And that's going to end up equaling. So we have our 400i plus 0j plus the 25i plus the 25 root 3j. And then adding the I and j value, so the I value is going to be 425i plus, and the j value will be 25 root 3j. Alright, so this is our true velocity. Awesome. We found the true velocity. What are we missing? We need the speed of the plane and the direction of the plane. Okay, well now, since we actually have the vector we want, we can use this to find the speed and direction, because we have the formulas for that. Once we have our vector, we can easily find the speed and direction. Once again, remember, the speed is the same thing as magnitude, and we know that formula. So speed, or magnitude, that is going to equal the absolute value of this, so it's going to be the square root of my a values and my b values. So my a value is the 425, and my b value is the 25. And then that'll end up with approximately equal to about 427.2 miles per hour. And then, lastly, we need to find the direction. Well, what is the direction? If this is our vector there, we're trying to find this angle here, theta. So if we drew a right triangle with the values that we know, we can find our theta. And if you'll recall, our A value is the 425, and our B value is, so we have our A value here, which is the 425, and our B value is the 25 root 3. Let's go ahead and write that right down here. So my direction, getting a little squishy, the direction is tangent of theta equals my 25 root 3 over my 425. And then, to find that, because we don't know that on the unit circle, we're going to have to take the inverse, so tangent inverse of 25 root 3 over 425, and we'll end up with theta is approximately equal to 5.8 degrees. So the plane wasn't put off that much by the wind. Okay, so you might say, well, shouldn't we be writing a sentence for this? You would not need to write a sentence for this one. It is asking for these values, and it's kind of weird to write in a sentence. So I would be fine for this type of a problem if you just went ahead and you boxed your values and you labeled them correctly. So once again, please make sure you're labeling them correctly. We have theta for direction, W with the little arrow for the velocity, and then the speed is the magnitude or the absolute value of your vector. A lot going on. So let's take a look at another word problem. A boat is launched from one shore of a straight river and needs to land at the point directly on the opposite shore. Let's just go ahead and draw a picture here real quick to figure out what's happening. So if I have two shores here, and let's say, I got the water flowing in between and whatnot, what am I looking at here? So I have a boat on this side, and I'm trying to get it so that if I shoot it across, it'll go straight exactly to where I want it to go on the opposite side. Now, the speed of the boat relative to the water is 14 miles per hour, and the current is flowing east at 6 miles per hour. In what direction should the boat head in order to land at the desired position? Okay, so let's say, for my drawing, that the river is heading in that direction. And what do we know about the river? It's heading that direction. How fast? 6 miles per hour. Once again, the speed is also considered the magnitude of our vector. Now, when we're saying relative to the water, this is talking about it not affecting it. Okay, so it's the water not affecting the speed on the boat, which would be 14 miles per hour. So let's go ahead and write down what we know so far and attach our variables to it. So let's write our let statement. So let's say let u, we're going to let u equal what? That'll be the boat. And what do we know about the boat? Well, the magnitude is 14 miles per hour without the water affecting it. And then v, we'll go ahead and let that be the current. And we know the magnitude of the current is 6 miles per hour. And what are we looking for? Well, so if I decide that I want to shove the boat off in some direction, I want to head it out a little upstream, right? So that as it's going upstream, the current can push it into the right position so that it ends up going directly straight across. So I want to find that. I'm going to call the green one W. And W is the resulting true speed of the boat. Well, once again, how do I find the resulting true speed? In order to find that, I need to first figure out the vector for my boat and for the river. And once I find those two together, then I can figure out W. So U, well, that is going to be the magnitude of U. Oh, I realized I wrote that wrong on the previous one up here. Those should have been the magnitudes of U, and that was V. Okay. Magnitude of U, cosine theta I, plus the magnitude of U sine theta J. And then I need the magnitude for V. So I need a magnitude cosine theta I plus magnitude V sine theta J. And do we know all of these values? Almost. Let's see what we know. Well, we know 14 miles per hour there. Oop, but that's missing an h for the miles per hour. And then the current, so the velocity, or not, sorry, the velocity. The magnitude for the current is a 6 miles per hour. And now let's see if we can find the theta values for each of these, or the directions for each of these. Well, I know the direction of the stream. That's heading straight down, so that's going to end up being 0. So my theta value will be 0 here. Now what about the direction for u? Well, you know what? That is what we're trying to find. We're trying to find what direction the boat should head to end up in the right spot. So theta is actually the value we're searching for. So let's go ahead and keep that in mind because we are searching for it. So u is going to equal, let's see, 14 cosine of theta I. We're not going to worry about the theta yet because that's what we're trying to solve for. And then v is going to equal, we have the 6 cosine of 0 I plus 6 sine of 0 j. And then, so simplifying that out, we're going to get that v is 6j. Alright, so what will w be? We don't know what theta is yet, so we're just going to go ahead, plug this into w, and see if we can figure something out. Well, w will go ahead and add up the, oh, sorry, that should be 0j. The I and j values. So we'll have the 14 cosine theta plus the 6 for the I values. Let me go ahead and highlight that with colors so we figure out, or we know where those came from. So that plus that is going to give me our value here. And then plus the 14 sine theta plus 0 j. And where did that come from? Well, that came from here. Oops, wrong color. Here and here. Okay, so we have our w value. And keep in mind, what are we searching for here? We are trying to figure out what the angle is for here. Now, what do we know about this direction over here for our w? Well, our vector here, we know that the a value is going to be 0 because it's headed straight up if we're looking at the xy plane. And we don't know what the b value is. But we don't actually need that. We already know that the a value is supposed to equal 0. And this here is the a value. So we know that that should equal 0. So let me go ahead and write this down. We know that, well, what do we know? That 14 cosine of theta plus 6 is supposed to end up equaling 0, because it's headed straight off in the upward direction. So we can solve this to find theta. Because remember, we're trying to figure out the direction. That is what our goal is. We're trying to find the direction. So all we need to do is get an equation with theta. So then we'll have 14 cosine of theta equals negative 6. Cosine of theta equals negative 6 divided by 14. Taking in the inverse, cosine of theta equals cosine inverse of negative 6 over 14. Once again, make sure your calculator is in degrees. And then theta is going to come out to be approximately 15.4. Awesome. So that is theta. But we want to figure out which direction the boat should head, so we have to tell it the directions in terms of north and south, like we've done before. So how would we figure that out? Well, the theta that we just found, if we're looking at our xy plane, the theta we have found is this direction here for our boat. So that is 115.4. But we're trying to figure out which way to tell our boat. So we want to find this angle right here, theta. How would we find that? Well, we'll just do 115 and minus 90 degrees from it. So when we take away the 90 degrees, we'll be left with the angle that we're looking for. So 115.4 minus 90, 115.4 minus 90 degrees is going to give me 25.4 degrees. And there we have our direction. The direction is going to be, well, we go north and then 25.4 degrees west. And for this, we will answer with a sentence. Alright, so let's take a look at the next thing. So vectors are also used to measure or to model force, such as the force of gravity pulling an object downward. Force is usually measured in newtons, which would be kilograms per meter per second squared. If several forces are acting upon an object, then the sum of the forces is called the resultant force. Forces are in equilibrium if the resultant force is zero. That means they sort of cancel each other out. Alright, example 9. Sketch the vectors. Find the resultant force of the vectors, and then find the additional force needed for the forces to be in equilibrium. Alright, so let's go ahead and first sketch the vectors. So we go ahead and scale our graph accordingly. It looks like the largest horizontal value we get is a 5, and the smallest is a -2. Largest vertical value is a 10, and smallest is a -1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. I'll go ahead and extend it a little bit. Then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, let's go ahead and color code these. I'll do F1 in green, F2 in red, and F3 in blue. Okay, so F1, our horizontal component is -2 and then up 5. So -2 up 5. 1, 2, 3, 4, 5. Right there, -2, 5. And then let's go ahead and take a look at F2. So +5, +10. 1, 2, 3, 4, 5. +10. There we go. And then F3, the blue value is going to be +3, -1. +3, -1. Okay, all of these are centered at 0, because we weren't told otherwise. Okay, so now what do we need to do? Well, we need to find the resultant force. What is the resultant force? That is the sum of the forces. Okay, which we are told right on up here. The sum. And what is sum? Sum is addition. Okay, so resultant force is going to equal F1 plus F2 plus F3. Well, that's just going to be -2, 5 plus 5, 10 plus 3, -1. Okay, so let's go ahead and add up all the A values and then add up all the V values. Alright, and then we get, so -2 plus 5 plus 3, that'll end up with 6, and then 5 plus 10 plus -1 will be 14. So there we have the resultant force. Next, what do we need to find? We need to find the additional force that requires the forces to be in equilibrium. So what does that mean? Well, that means the resultant force should come out to be 0. So we need to figure out some value. So let me just go ahead and call this, this is supposed to be equilibrium. So we need to figure out some value, AB, such that when I add it to the resultant force, 6, 14, I end up with a force of 0. So the answer should become a 0. Well, this is just like solving some sort of an algebra problem. So let's go ahead and add up our A values and add up our B values. And we'll have A plus 6, comma, B plus 14. Somehow we need that to equal 0, 0. So let's create our little mini algebraic equation here. So we know that A plus 6 somehow needs to equal 0, and B plus 14 somehow needs to also equal 0. So A plus 6, figure out when that equals 0, and B plus 14, when does that equal 0? We'll get an A value of -6 and a B value of -14. And that is going to be our equilibrium. Our equilibrium is going to be -6, -14. That is our vector of equilibrium force for the sum. Alrighty, that is it for 9.1. Please email me if you need any help or would like to set up an office hour.